always take. Yeah. Excellent. Okay, we're ready to go here this morning, or well, in afternoon for many of us joining us. So without any further ado, welcome to Schedule B of the Monsoon Seminar Series for 2022. And this week, we are joined by Dr. Kenji Matsuzaki from the University of Tokyo. And so please make sure to put in any questions you have in the chat, just so that everybody can read them and see them. And then I'll call out on you to basically ask a question, or I'll read it out for you. And so without any further ado, Dr. Matsuzaki, could you basically tell us a little bit about the late Miocene and marine ecosystem?
Yeah, okay, so thank you very much. So just one question, shall I turn off the video when speaking, or
you are free to do whichever makes you the most comfortable.
Okay,
the rest of us will keep videos off, but
okay,
yeah.
Okay, so well, I will leave it like this. Okay, so thank you.
Perfect. Cool.
Yeah, okay. So thank you for the invitation. So today I will just show you what I've done in the Japan Sea since 2016. It's almost 6 years that I'm working with the Miocene sediment of the Japan Sea. And through this talk, I just try to summarize what I've done during this 6th year. So I focused in this research on the late Miocene because there is a newly very famous global cooling, which is called the Late Miocene Global Cooling, which spanned from 7.8 to 5.8 million years ago. And this event is characterized by a cooling of the mid to high latitude of both hemispheres. As you can see here in the northern hemisphere and the southern hemisphere, you have a SST drop of between 5 to 10 degrees, while in the tropics, this cooling is very minor, as you can see, only 2 to 3 degree decrease here. But SST decrease is not the unique feature characterizing this cooling event. So this is for a compilation of carbon isotope. As you can see here, there is also a huge decrease in the global carbon-13 of the deep ocean. And many discussion was done for try to explain this decrease in the carbon pump, but based on the paper I have read until now, there is no clear consensus. There are some people arguing for biogenic bloom. There is other arguing for change in vegetation. So I think it's not still a resolved issue. However, just when you have this decrease in carbon, it is true that you have a huge vegetation changes in the world, in particular in Africa and East Asia, where you have the rise of C4 plants and the rise of vegetation, more characterizing dry area. And in Asia, about the climate, there's also many studies which have been done around here, and there are many. So I just present the two research I've selected, but it's two among many. So this is a research done in the North China. It was conducted in lake, and they did many magnetic susceptibility analysis of the record of the sediment collected from the lakes. And because based on modern calibration, this data fit infer, as you can see here, precipitation. Here it's the precipitation year. They suggested that between 8.5 to 7 million years, you have a relatively wet climate in northern Asia, while since 7 million years, it's likely that you have a more drier climate. And they propose the weakening of the summer monsoon here. And now I will show some its ocean data. Is from the Southeast Asia in the South China Sea. It's a compilation of many data such as oxygen isotope. You have hematite goethite ratio and aeolian dust coming from a previous study which based on estimation. But here also there is some evidence showing that from 7 million years there is an increasing deposition rate in Aeolian dust, which suggests that the winter monsoon get intensified at that time, which is in agreement with the weakening of the summer monsoon in North Asia. So the first step, what I wanted to do here is to try to monitor such changes in the monsoon, but in the Japan Sea, because the Japan Sea is a very particular area. It's a marginal sea of the Japan Sea, so this is the characteristic of the Japanese oceanography now, but the most important thing is that it's highly influenced by the monsoon. So by doing an analysis over there, we thought that it is possible to reconstruct monsoon variability during the Miocene. So this is what we target in the first stage. So first we try to monitor the dominant monsoonal change between the Miocene, in particular between 9 and 5 million years in the Japan Sea. And for that, we need an accurate depth age model. So this is the first step. So preliminarily, we did there were biostratigraphy depth age model, and based on this biostratigraphy depth age model, there were tuning of the sediment gamma reattenuation rate to the Milankovitch cycle for try to get the most accurate possible depth age model for try to constrain well the monsoon variability during the Miocene. And the next step, what you need is proxies, but in the Japan Sea there are a few problems, but because the CCD is very shallow, so there are not many calcareous microfossils, so all calcareous microfossil based geochemistry is not very likely possible here. So most people try to do something with sediment mineral composition, also trace element geochemistry. And because it's mainly because I'm a micropaleontologist, but I propose a new semi-quantitative approach for try to reconstruct the monsoon. I propose to analyze Radiolarian microfossil because they are very well preserved in such sediment. So I don't know if you are very familiar with Radiolarian, but they are holoplankton. Their size from 0.03 to 2 millimeter. Some tropical fauna bear algal symbionts, and they bear a skeleton based on biogenic opal. So they also have the potential to be used for discuss variation in the silica cycle. So what I've done for my first research was to try to develop this microfossil as a paleoceanographic proxy in the North Pacific. So via many offshore expeditions in the North Pacific, I analyzed plankton samples from the surface to the deep water, and I get to the conclusion that this is more likely the vertical distribution of Radiolarian in North Pacific. So it's very well stratified. You have surface, intermediate, and deep water species, so it can be very useful for reconstruct shallow to deep water marine environment, in particular in area where you do not have carbonate. Then we also need to know where species live. So as a first step, I try to clarify their biogeographic distribution. This is what I've done here with this group here. So the conclusion is that you have species who live in the subtropical area, transitional area, and subarctic area. So it can be used for paleoceanographic studies. And for the mass, but when you deal with very old sediment, the problem is that you do not have many information about where the species do live and about their ecology. But the good point, as you can see with this with this figure which showing the number of species since the Mesozoic. So the Miocene is here, and as a summary, you have almost 250 Miocene species still extant. So we probably know the ecology. So paleoceanographic studies of the Miocene based on this proxy should be possible. So the first step, what I wanted to do in the Japan Sea is to know how the sea surface temperature has changed at that time. And because no forum I tell before, so magnesium, calcium not very possible. So I tried to apply a kind of multiple regression analysis for try to get sea surface temperature for the Miocene, only relying on extant species. But the problem is that because there is no high diversity in the species in the Japan Sea, so we had only 8 extant species groups. So we did some statistics for try to get a quite suitable equation for discuss changes in sea surface temperature in the Miocene. But even if we can have a temperature base using this equation, we have to know what this temperature means. So for that we first proposed to apply it on quaternary for the quaternary, and this is the figure you have on the left. So in the left part above you have the sea surface temperature obtained from the equation I've shown you above using Radiolarian. This is it is also an IODP core, but collected in the East China Sea for the Pleistocene. And here you have the normalized mean grain size obtained from the Chinese Loess Plateau. And here you have the age. And as you can see here, the blue band indicates glacial periods. So during glacial period, for the quaternary using the method above, you have very low sea surface temperature, which correspond to period of strong winter monsoon. So it is likely that based on this method for the quaternary, you can reconstruct sea surface temperature, which fluctuate according to the interglacial cycles, and low SST seems to be related to strong winter monsoon. And for further support that hypothesis, we propose to discuss the seasonality of Radiolarian in the Northwest Pacific. So this is the flux of the daily flux of Radiolarian species in northern Japan. And there is as you can there is very few peaks, but the highest peak is reached in December. So it is likely that Radiolarian is more likely inferring condition during winter. So we associate the Radiolarian temperature to winter SST, and thus it fits well with what we have on the left, which is strongly related with the winter monsoon. So all the preliminary done, now we propose to reconstruct the sea surface temperature of the Miocene in the Japan Sea. This is the sea, here Japan Sea. This SST profile is what we get from Radiolarian, and we then compare it with the benthic carbon profile and oxygen isotope profile obtained from the South China Sea, and above you have alkanon SST obtained from the south of Bering Sea and the Northwest Pacific. It is a Shatsky. So the key point was that we have a strong cooling in Radiolarian SST from 7.9 to 6.5 million years, where the temperature decreased from 24 to 16. And this cooling is very synchronous to what you have in the carbon profile in South China Sea. And this is also very similar to the cooling observed in the Bering Sea. So if you just look at the Radiolarian curve, and based on the assumption we did previously, it will infer that we have a cooling in the winter SST due to a strong East Asian winter monsoon between 7.9 to 6.5 MA in the Japan Sea and in the Japan Sea. But if you look, for example, here at Shatsky, same latitude, you do not have the cooling is much later. So for try to discuss this disparity, well, we just check when you have the maximum bloom of nanos in the Northwest Pacific. It seems that alkanon bloom are higher in spring to summer. So this discrepancy may be related to disparity in the season. The summer cooling may happen later and the first you have and the Late Miocene Global Cooling is first characterized by a strong winter cooling. This is the hypothesis we get in the first step. But also the Japan Sea is also characterized by tectonism, and about 7 million years it is likely that you have a very shallow seaway here which allowed inflow of warm water, and this seaway likely closed around 7 million years. So it is also we suggest that the closure of this seaway around between 7 to 8 million highly amplified the cooling observed in the Japan Sea, and also may contribute to the drastic cooling we recorded above. So here it is the summary of the first part, where we show that the Japan Sea recorded an 8-degree cooling between 7.9 and 6.6 million years, and this cooling was probably amplified by tectonic. Now, in the second part, I wish to focus on the changes we had in marine biosphere, because during the LMGC, which is about here, you have many turnover in macrofossils, in macrofauna, and here I show, this is the case of the Balenidae, as you can see here, with the decrease of the ancient type of whales instead of the more recent type of whales. But this is just one example among others. There is also many other marine mammals who evolved or changed at that time. So it is likely that there is a drastic change in the marine mammals during the Late Miocene Global Cooling. And if you get another focus, this is for the shark, a megalodon, as you can see here. This is the distribution of this shark until 5 million years. It is present, and this is its distribution between 5 to 2 million years, and you can see the Japan Sea is here, and it is likely that during the Late Miocene Global Cooling, this shark stopped to inhabit the Japan Sea. And at the same time, you have another mammal who inhabited the Japan Sea coast who disappeared during this time interval. So yes, during the LMGC, you get a drastic macrofaunal turnover here, and changes in the monsoon mode. As previously we showed that we get a dominance of the winter monsoon since the LMGC, so it is possible that the cooling and the drying of East Asia may cause this great faunal turnover. But we propose to discuss it a bit more in detail, because if you look, for example, at the Radiolarian fauna, you have an endemic species. This one is the name is like this, but this species only inhabit the Japan Sea between 10 to 7 million years, and it disappeared during the LMGC. And because it's endemic to the Japan Sea, we proposed before that it may inhabit deep water of the Japan Sea, and was isolated with the North Pacific, because you have a strait here about 1,700 to 1,000 meters, and which isolate the species geographically. But if it's really the case, monsoonal change may not likely affect deep water. So deep water, it's more related to, it's more surface processes. So we suggest it is possible that there is a kind of change in deep water exchange or circulation in the Japan Sea at that time as well. So this is what we propose to clarify here. And yeah, so we propose to clarify deep water provenance of the Japan Sea between 9 to 7.5 million years. It was already reported that during the LMGC, the NPIW get intensified and likely influenced the bottom water of the Japan Sea, causing a great oxidation of the bottom water, which is likely different from what you have for the time interval older than 7 million years. So what we will discuss now will likely agree this study, but we propose another approach. We focus on an extant deep water Radiolarian. So this is plankton data I collected here of the Northwest Pacific. We get plankton tau from 0 to 3,000 meters, And we want to focus on this species, in particular those in red, because this is the two extant species occurring in the Miocene sediment of the Japan Sea. And this is the profile of this oxygen profile of this area, of the point I've shown you just before. So here, from 1,000 to 3,000 meters, which correspond to water depth with low oxygen, dissolved oxygen, and we associate this water mass to the Pacific Central Matter, which is originated from the Southern Ocean, which is very nutrient rich but poorly oxygenated and quite salty. And at this water depth, this Radiolarian is abundant. While above, for example, 500 to 1,000 meters, which is more oxygenated, and as you can see here, the salinity, very low saline and very low temperature water, you have this species which is very abundant, and this water mass actually corresponds to the North Pacific intermediate water. So now we propose to discuss change in the accumulation rate of these two species for try to discuss the deep water provenance of the Japan Sea at that time. We will also use another species for relate it with the changes in the surface, which is this species, which is an extinct species, but as you can see here, before the Late Miocene Global Cooling is restricted to the very high latitude, and with the Late Miocene Global Cooling it shifts until the mid-latitude. So this species can be used for monitor the southward shift of the subarctic front. So now we'll show you the main data. So we'll propose to focus on this curve, the PCW index. This is the species I've just shown you before, which is related to the Pacific Central Water. So as you can, so its accumulation rate vary from 0 to 5,000, and high abundance of this species, as you can see here, most likely occur when the eccentricity is low. So it is based on this graph figure, we can say that it is likely that the Japan Sea is influenced by very deep Pacific Central water from 9 to almost 8 million years, and its inflow are regulated by the eccentricity, and it is likely that you have higher inflow of this species when the eccentricity is low. And in here I've plotted down the endemic species I've just told you before in green, and the endemic species occur interestingly just when you have inflow of Pacific Central water into the Japan Sea. And its high flux also is likely based by a kind of eccentricity, and more likely occur when the eccentricity was low. So based on this, we can think that the endemic fauna occurrence in the Japan Sea was likely related to the inflow of the Pacific Central water, at least until extinction at around 7.4 million years. This figure is not so important. We just show the main Milankovitch cycle influencing the inflow of the PCW, which, as you can see here, you have the 200, 120, and the 40 kiloyear cycle here. So these two cycles are the classic obliquity and eccentricity cycle, and the 200 cycle is a bit more particular, but in recent paper it was associated to a particular eccentricity cycle. And in the endemic fauna, we do not have the obliquity, but you have a kind of eccentricity cycle which is quite prominent from 8.9 to 8 million years. And in the slide before, we saw that we have inflow of Pacific Central water during low eccentricity interval, and this inflow is likely necessary for the endemic species to bloom in the Japan Sea. So now we just propose to discuss what is the mechanism which causes the PCW inflow into the Japan Sea, and why it occurs mainly when the eccentricity is low. So for that, I will mainly rely on Horburn et al. 2013 EPSL paper, and it was suggested that during low eccentricity interval, this is the lower part of the figure here, you have an expanded ice volume, an expanded ice cover, and this will create an enhanced ventilation of the regional intermediate and deep water, which will in turn strengthen the Pacific meridional oscillation, and thus we will have a more intense production rate of PCW water. And this occurs during low eccentricity, while when the eccentricity is high, because it's warmer, you have less ice, the ice sheet is smaller, you have less ice cover, so the Pacific meridional overturning circulation is lower, and thus lower PCW production rate. So this idea is very interesting because it fits well with our record, and it will suggest that you have Pacific central water inflow into the Japan Sea during low eccentricity because of an expanded East Antarctic ice sheet and its related ice cover. So, So we have explained this curve. So this curve, it just means that you have influence of Pacific central water when the Antarctic ice sheet is quite big, which will strengthen the Pacific meridional overturning circulation. And this will, in part, allow the blooming of an endemic species. But this of an endemic species, this is what I told you just before, but we check how both curve species are correlated. We only have a Spearman index of 0.55, so it means that yes, the endemic species is partly related to the inflow of the PCW, which is related to the PMOC and low eccentricity. However, you should have other mechanisms for clouding it blooming. But because we do not have many strong evidence for that, but because at that time the winter monsoon was weak, so we suggest that the summer monsoon was pretty strong. So as a speculation, we propose that the occurrence of this endemic species is related to both PCW inflow due to strong PMOC and probably to local water influenced by the summer monsoon, and probably the end of the weakening of the summer monsoon around here is one of the factor causing this species extinction, but the monsoon is not likely the main factor causing the decreasing inflow of the PCW water into Japan Sea, and this is the reason we want to discuss now in a second part. So from 7.5 million years, you have a decreasing sea surface temperature, decreasing PCW species inflow, and the extinction of the endemic fauna. Instead, you have an increasing flux of impaired W species and increasing fluxes of species which infer migration of the subarctic water. So how to explain this factor? So the first, we have to consider the tectonism, because as I show you here, here you have our studied site is here, and from 10 to 7.5 and from 6.5 to 4, you have an uplift of the east part of Japan, which cause we have more land, and also you have a shortening of the strait about here. And previous studies suggested that this strait actually showed from about 1,000 meter to 500 meter at between 10 to 4 million years. So it's progressive. It cannot occur rapidly, but progressively you have a shortening of this strait from 1,000 meter about 10 million years to 500 meter about 4 million years. So we suggest that the tectonism should be of importance, because as you can see, the PCW here, well, it's up to the area. So here is about, the latitude is about 35 to 40. So for example, if the seal depth gets shallower from 1,000 from 1,000 to 500, it will automatically prevent PCW inflow. So as a possibility, we suggest that the tectonism may be one factor which stop PCW inflow to the Japan Sea. But there is also another important factor. It's here. Here, as you can see, it was it's the carbon isotope curve from the Southern Ocean compiled in Harbor 2016. So I think here it's intermediate. I do not remember which is what, but the red, green, and blue indicate carbon isotope from the intermediate and deep water of Southern Ocean. And the important thing is that from 7.5 to 6.5 million years, there is almost no gradient between the intermediate and deep water in the carbon isotope signal in the Southern Ocean, which was associated to a decreasing ventilation, a weakening in the ventilation of the Southern Ocean, which will in fact cause a weakening of PMOC. And if PMOC is weakened, automatically you will have a lower production rate of PCW, and the Japan Sea may have been sensitive also to this event. And actually, this weakening of the PMOC might occur between 7.5 and 6.5 million years, which is over there. So as you can see here, it is 500 kilo years after the first decrease in PCW species here, but so this part might likely related to tectonic, but for this part where you go almost to zero, it is likely that the PMOC weakening was the last event causing that the Japan Sea was not influenced anymore by Pacific Central water. And for support this hypothesis, after 6.5 million years, when you have a recovery in the ventilation of in the Southern Ocean, in the Southern Ocean deep water ventilation, there is no big change here. So which means that from here to here, the northern strait of the Japan Sea continued to shoal, and it was probably too shallow. Once it was recovered from the weak PMOC, it is likely that because of tectonics, the northern strait was too shallow for allow high PCW inflow like before. So this is how we interpret this result. And for this data, well, it was already discussed many times, and it's not so new, but we just say that we are in a close agreement with Late 2021, and it is likely that during the LMGC, there is an increased production rate in PNW water, which became the unique and dominant deep water influencing the bottom water of the Japan Sea. And it was probably related to the increase to the inflow of the subarctic water, which, as you can see here, high peak occur every 200 or 400 kilo years, which can be associated with a winter monsoon signal. So we propose that strong winter monsoon cause a southern shift of subarctic front in the Japan Sea, and on the other hand, in North Pacific, because of the global cooling, you have an increased production rate of North Pacific intermediate water, and the Japan Sea likely more shift from a temperate subtropical summer monsoon climate oceanography to a more subarctic climate oceanography around 6.5 and 7.5 million years. So now I just wish to summarize this part. So until 7.5 million years, we propose eccentricity-based PMOC allow inflow of Pacific Central water into the Japan Sea, and it is more probable that a mixing of PCW water with local water influenced by the summer monsoon allows a blooming of endemic fauna. And since 7.5 million years, it is likely that both tectonic of the seal depth of the northern strait and a weakening in the PMOC due to a reduced ventilation in the Southern Ocean prevented PCW inflow into the Japan Sea. Instead, the EAWM, which is an oxygen-rich intermediate water of the North Pacific, became the dominant deep water influencing the Japan Sea. And the winter monsoon, may allow a pointing of the EAWM, but I'm sorry, I forgot to discuss this point. That's all I have for today. Thank you.
Great, thank you. So let's see, I just need to, there we go. Okay, so please remember to type in any questions that you have in the chat for our speaker today. I do have a question for you as everyone's gathering their thoughts. So you have some great data in terms of the temperature and the ventilation in the Japan Sea, kind of, I think, on a local scale with the kind of geographic distribution of some of your species, as well as kind of broadly. So do you have any evidence for salinity from any of your Radiolarian species, either locally with increased winter monsoon discharge or with maybe changes within the Sea of Japan?
For the shallow water you're speaking,
yeah, probably shallow water.
But
again, I understand. Yeah.
I did not plot it here for how to say. So, so I will go to the slide. I have this type of data with other. Here I mainly focus with the deep water, but yes, we how to say that? Well, I do not have the data in this PowerPoint, but for example, when you can see in this SST profile, when you have, for this period, when you have relatively high sea surface temperature, you have high flux of species tolerant to low salinity and warm water. Yeah, actually.
Cool.
But they are not related to. Yes.
Cool, great. Yeah, just because the fact that you have such an intensification with such change in temperature, I think it would be just there's a lot going on.
But actually, yes, this cooling can be associated with also an increased salinity, because from about here you have you do not have you do not have species with high temperature and low salinity tolerant species. You shift from subarctic fauna at this boundary.
Oh, cool.
So it's also consistent with the winter monsoon intensification, I think.
Nice. Yeah. Great, thank you. Yeah. Oh, I see that Anne has her hand raised. Anne, would you like to ask your question?
Yes, good morning. Thank you very much for this really interesting talk. I'm very curious about this North Pacific influx of water masses. I think it's very exciting because we know so little about the North Pacific circulation in the Miocene. And in terms of the Radiolarians, what would be why would you have a specific assemblage of Radiolarian associated with this water mass from the North Pacific?
Sorry, I'm not sure why I have are you speaking about this graph? This figure?
Yeah, I'm curious about why you would have a specific assemblage of Radiolarian.
Are you speaking about the ecology?
Yes.
Oh, okay, thank you very much. So it's a very complicated question.
Sorry.
Here it's just observation. I looked at the plankton samples, and of course, when you look at the plankton, you have very high diversity in the upper layers with many species, and when you go down, you get automatically very few species diversity. And the species today, at least, prefer these water depths, so which, as you can see, is very salty, very oxygen poor. So as a hypothesis, it might be that they may have shifted to the deep in water depth because of the high probably competitivity in nutrient in the in the shallow water. Did I answer you or
Yes,
not really?
yes,
Yeah, I think it's more related to a migration due to high competition for get food.
Mhm.
Normally.
Thank
But
you.
if you just look at the database, it can be it can be used for tracer of this water mass at this time. And the most interesting thing is that if you go in the lower latitude, when you get more sustained influence of the subarctic water, this species abundance in the surface sediment is higher than when you go in the high latitude. So I think that it's quite suitable proxy for try to monitor these water depths, these water masses, I'm sorry.
Okay. Great. Thank you very much.
Yeah, thank you.
We have a couple of comments in the chat.
Oh, really? I did not see it.
From Mark and Antje.
Oh, thank you.
Complimenting.
Yeah. Thank you. Yeah.
And then so just if anybody has any other questions, please come in or raise your hand in Zoom. So I had another question. Considering the amount of data that you have, were you able to establish any type of biodiversity metric at all, or is that kind of beyond the scope?
Biodiversity, well, yeah, of course, yes, because if we count each species, it's possible to provide such type of data, yeah.
Okay.
However,
cool.
I did not, I'm sorry.
Okay, there's only so much you can talk about.
Yeah, it's possible, but yeah.
Great.
Okay.
We'll get everyone a moment if they have any other questions. Okay, well, thank you so much for your talk today, Kenji. You have a wonderful talk. Again, great, excellent data. It's really cool to see what's coming out of your lab. And so before everybody runs away, oh, wait, that's a applause hands, not a... So before everybody runs away, please remember to attend the talk that is next week on the 9th of February for Mahyar Matadi. And with that, I hope everyone has a great rest of your day. And again, put your hands together for the speaker.
Thank you, bye.
All right, thank you. Bye, everyone.